All right, this is a video to finish the last two examples in section 1.4 and then to look at section 2.1. So this one was what we were learning about the rationalizing of an expression where we have two possible terms in the denominator. And we learned that we want to use the conjugate, that's what we called it, if you look at our previous example, of our denominator to clear that out. So the conjugate of this denominator would be a square root of 5 minus 4. And whatever we multiply by on the bottom of our fraction to change it, we're going to do the same thing on the top. That's like multiplying by a 1. So now we're going to be foiling all of this out. So on the bottom, we get the square root of 25, which we'll simplify in just a minute. And we'll have a negative 4 times the square root of 5. Then we'll have a positive 4 times the square root of 5. And then we'll have 4 times negative 4, which is negative 16. On the top, I'm going to have square root of 3 times square root of 5 is square root of 15. Square root of 3 times negative 4 is negative 4 on the square root of 3. Negative 4 times square root of 5 is negative 4 square root of 5. And negative 4 times negative 4 is positive 16. We want to add the like terms in the bottom and then reduce this perfect square right here. So that's 5. So that means my denominator is 5 minus 16 or negative 11. On the top, I don't have any like terms. I'm just going to bring that over. Oops. Added an extra minus sign in there. This is just going to be the top. We can't add any of them. None of them are like terms. We can, if we like to simplify this a little bit, we don't usually like a negative in our denominator, so we could bring that out to the front. So even though this doesn't look pretty, this is the rationalized version of that original expression. Okay, so we got rid of all the radical parts in the denominator. All right, let's look at the second one that we didn't get to. So for this one, it's just like what we were talking about earlier. It looks like a big, scary factoring problem. I always focus on getting those monomials separated out and multiplied together first. So 2 times 4 is 8. Then I bring down my 3x plus 2 to the negative 4 and 4x minus 5 to the 1. I'm going to over-exaggerate that plus sign there. Negative 2 times 3 is negative 6. Then I will bring down the 3x plus 2 part first so I can see it in the same order. And a 4x minus 5 squared. When we talk about what do we have in common, the only thing really different about this problem that makes it a little trickier than the previous one is there are these negative exponents. If you look back at our general rule, though, it helps to see why I'm going to pull out what I will in just a second. And I'll also show you what's happening on the side when we look at this. So when we looked up here, we were just kind of calling it triangle and circle, remember? We always pulled out of the two exponents, if we say a triangle in both of them, we always pulled out the smaller one because that's what they have in common. The smaller numerical exponent is what they have in common. So when you're looking at these that have negative exponents, negative 4 is a smaller numerical number than a negative 3. If you think about a number line, negative 1, negative 2, negative 3, negative 4, 0, 1, 2. This is smaller on the number line than the negative 3, okay? So anytime you're pulling out like GCF common factors with exponents, we always pull out the smaller of the exponents as long as every term has it. Like that was part of our rule. So I'm going to pull out a 2 for the 8 and the 6. They have that in common. I'm going to pull out the negative 4 because that's the smaller numerical exponent for the 3x plus 2 part. 4x minus 5 is more like what we saw. So they have a 1 in common. Again, notice smaller numerical exponent is what gets pulled out. We're going to have a bracket left. We're dividing these out of each of these. So 8 divided by 2 is a 4. Negative 4 of these, we pulled out all negative 4 of them. So think about that. Remember, this is really just meaning it's in the denominator. That's all these mean. So when you're pulling out these negatives, you're actually pulling out terms that are going to go in our denominator at the end. So we have 3x plus 2 is not going to be in the first term, but we have, and neither is the 4x minus 5. We ended up pulling out both of those in this first one. Then we're going to be dividing -6 by 2, so that's going to be a -3. Realize these are not able to be added together because this might still have other terms attached to it. Now, I wanted to show you this one. Remember we said in class when we're pulling out a GCF, we are dividing it out. So this is the original piece. I'm dividing out that what we called the GCF of that, which was the 3x plus 2 to the -4. So if you think about that, that same base, we subtract the exponents. So when we're dividing it out, we're really subtracting those exponents. And if we subtract those exponents, we do numerator minus denominator. It's minus a -4. So it ends up being a +4 for that part. So that'd be -3 plus 4. In other words, we get 3x plus 2 to the first. Another way of thinking about this is think about if you're looking at it as a division step, which is what we do when we factor out a GCF, you can just think about flip-flopping these because they both have a negative exponent, so they're both in the wrong location. So that would put the 3x plus 2 to the -4. It would be up to the 4th on the top. This one would be on the bottom as a +3, and then we would reduce or cancel out. So when you pull out negative exponents, you just have to remember you're dividing out that part. So you're going to be doing subtraction from the exponent. So that's why -4 minus a -4, that'd be 0. That's why we don't have one of those. But -3 minus a -4 that we're pulling out for the exponent part, that's going to be -3 plus 4. So we are going to get a 3x plus 2 to the first power. And we also have a 4x minus 5 here because we only pulled out one of those. So this one's a little bit not so nice to clean up on the inside part. We're going to have to FOIL this. So, and you cannot do 4 minus 3 here. That is not 4 minus 3 because this is connected by times over here. So this is going to be 4. I'm going to leave my -3 for now, but I'm going to FOIL this out. So that's going to be 12x squared minus 15x plus 8x minus 10. Just going to kind of work this out in this pink color for a minute. That's going to be 12x squared minus 7x minus 10. You need to distribute that -3 before we can do anything with the 4, because again, this is connected by times. So that's going to be minus 36x squared. Negative times negative will be positive 21x. Negative times negative will be positive 30. So what I'm getting so far is I have a 2 out front. I'm going to move that other guy to the bottom because he's a negative exponent. 3x plus 2 to the 4th. I have my 4x minus 5 to the first on top. And then I'm going to have this simplified. So that's going to be a negative 36x squared plus a 21x plus a 34. Now, the only thing else we could do to maybe make that a little bit nicer looking for the trinomial part would be to pull a negative out of that piece. So this technically, I think WebAssign will accept this part if you put it in, but you could pull a -1 out of the trinomial, bring it to the front, multiply it by the 2 up front. That makes it -2. And then remember, that would just change the signs of the trinomial. So 36x squared minus 21x minus 34 all over that 3x plus 2 to the 4th. Okay. So that's an alternative way to write that if you want to not have that leading term be negative. I do think WebAssign, because these problems are such a longer set of problems, they sometimes accept them in any format that is equivalent. Okay, so that finishes up the 1.4. So let me switch over to 2.1. We're looking at solving equations, and specifically the video that was the pre-video focused on solving equations that were linear in nature. They might have had some fractions or issues, but we were solving kind of basic equations. So you'll want to watch that if you haven't yet, but this one we're focusing on what is a bigger topic kind of for Math 136, which is solving rational equations and talking about their domain and whether or not their solutions actually work once we've solved them. Plus, we'll look at solving some literal rational equations. Those are ones where everything is usually a variable and you're just resolving it for another variable. So if an equation contains rational expressions, we often eliminate the denominators by multiplying both sides by the LCD, or least common denominator, of those expressions. Is if we multiply, now by doing that, the problem is you're clearing out your denominators, you're clearing out dividing by zero, essentially things that could cause an issue. So anytime you multiply by an LCD in an equation to get rid of fractions, you need to make a note off to the side what values that we've cleared out are unacceptable answers for our final equation. So I'll teach you how to do that in just a second. If we multiply both sides by an expression that equals 0 for some value of x, then the resulting equation may not be equivalent to the original equation, as illustrated in our examples below. In this process of solving an equation, we may obtain as a possible solution a number that is not an actual solution to the given equation. So by clearing everything by the LCD, you can create what we call an extraneous solution. It's a solution that doesn't work because it's outside of our restricted or undefined values. So I'm going to kind of walk you through the steps of how we solve these types of equations. First thing we do is determine that LCD of the rational expression and write down any values that make those variables in those terms equal to 0 for that LCD. These cannot be solutions because they would yield at least 1 0 denominator if you put it back into the original equation. Multiply each term of the equation by the LCD to get rid of the fractions, simplify, and then solve normally like a regular equation. So getting x by itself, or factoring if it's quadratic. The solutions of a given equation are the solutions found in guideline 4, with the exclusion of the values that were found in guideline 2. Okay. Now, if you have a set of problems where you just have a single fraction on each side, you can do what's called cross multiplying proportions. So most people know this property, A over B equals C over D. One fraction on each side equal to one fraction. That has to be set up like that to use this. Then you can cross multiply. You can say AD equals BC and solve. Okay. So because that first couple problems I have here are set up that way, we can solve them using cross multiplication. So this would, and it has to be an equal sign between them to do this. So we multiply the diagonal. This would be 3 times 3x plus 1 equals 9. I usually like to put my monomial in first, times 7x minus 2. Now, before I go any further with this is what I meant about, still need to write that LCD down. It would have been each of those binomials. That would be our common denominators if we did the LCD method. That means why that's important is there's some undefined values that we can't have as solutions to our equation because they would make us divide by 0 in the original problem, which is not, it's undefined. So you set each of those equal to 0 to figure out what solutions are not possible. So we can't have 2/7. We solve that for x. And also, if I solve this one for x by getting x by itself, subtract 1, divide by 3, I can't have -1/3 as a solution. So if I get either of these as my final solution when I solve this, it's not a true solution of the original equation. So let's multiply this out. This would be 9x plus 3 equals 63x minus 18. I'm going to subtract 9x from both sides, and I do not write that step because it's not mathematically technically correct to just have floating things underneath your equations, like adding something to both sides. So I just do it on my calculator and write it down. If you need to write it, I'm not going to count it wrong. It's just I want to model for you more how a mathematician would write their equations. So this is 54x by subtracting the 9x over. I'm going to add the 18 over to get it away from the x term. So that's going to be 21 equals 54x. And then this part's okay to show since it is technically dividing it in this step. We're going to divide by 54 so that we can get our x by itself. Now we do want to ask if that's a reduced fraction or not. 54, I believe, is divisible by 3. Yeah, by 18. So 21 divided by 3 and 54 divided by 3, doing the same thing on top and bottom, that is a 7/18. Now that is not one of my restricted answers that I can't get, so this solution should be valid. It should be okay. So 7/18. And we do not want to write that in decimal form. I know some people I saw doing that on their WebAssign for some of the earlier problems. You do not write answers in decimal form if they have to be rounded without rounding directions in the actual problem. What I mean by that is if you get like 2.5, that's 2.5. That is technically still the same thing as 2.5. But 7/18, if you type that in on your calculator, you can't write 0.39 because that's not exact answer anymore. You've rounded. So you need to write it as 7/18. Most of the time, unless there are rounding directions that tell you what decimal to round to, you should leave all solutions that are fractions as reduced fractions. Okay. For this one, we're going to use the cross multiplication method again, since it is just one fraction on each side. So I've got to write what my undefined values are for that LCD if I was going to get rid of that using the LCD method, just because that's always part of the restricted solutions. So I have two different binomials again. We'll add 3, divide by 10. So we do not want 3/10 to be a solution. That will make this denominator 0. 2x plus 3 equal to 0. We don't want that to happen either. So if we subtract 3 and divide by 2, we also do not want to get -3/2 as a solution for this equation, because that would make this denominator equal 0. So I'm going to write my cross multiplication step. I would have 5x plus 2 multiplied by the 2x plus 3. And then I'm going to multiply the x minus 8 times 10x minus 3. We're going to distribute all of this. So that's going to be 10x squared, 15x, 4x, and 6 on this side. The other side, we get 10x squared minus 3x minus 80x plus 24, just multiplying everything out. Combine like terms on the middle parts of each of these. That's going to be a 19x in the middle of this side on the left. The right side, we're going to have negative 83x plus the 24. Now, when you go to move the 10x squareds to be together, because usually when you have an x squared in your problem, you want to get everything on one side. But as soon as we do that, the 10x squareds cancel each other out. So if you subtract 10x squared from one side, and you have to do it to the other side as well, they both end up equaling 0. So there's not going to be anything there. Now, to add and get the x's by itself, I would add the 83x over if it was me, since it's a minus over here. So 19 plus the 83 is 102x. I'm going to also, in this same step, go ahead and subtract the 6 over to the right. So that would be 18, I believe. And remember, you divide by the number in front of x, not just the small number. We divide by whatever needs to be disconnected from x. So I'm sure I can reduce that. 102 divided by 2 is 51. 18 divided by 2 is 9. I think something bigger goes into both of these. I actually think 6 goes into both of them. Yeah, so if we divide this by 6 on top and bottom, then we would have 3 over 17. So my x equals 3/17, which again is not one of my restricted values. So I'm okay with that solution. All right, now we're going to get into some problems where we actually don't have the proportions. We don't have a single fraction on each side. This side has 2 on the left side. The first thing I usually do in situations like this where there's a minus kind of hanging out front of a fraction is I'll put it up on top. I'm going to go ahead and factor this denominator so I can see what my LCD is going to be. So I'm going to pull out that 3. Okay, so when I look at all of my denominators, I see I definitely have an x minus 3 that we're going to need to get cleared out. I also have a 3 and a 6. When you have two different numbers, you find the number that they both go into. So since 3 goes into 6, we can use 6 as our LCD, because when we multiply everything by 6, it'll divide evenly by both of those numbers. So what the LCD method says, because we haven't actually used the method yet, since those other two were proportions and we could cross multiply. But because this is not a proportion, it's not one fraction equal to one fraction, I'm going to use the LCD method. So what we do is we write what our restricted values are first. So x minus 3 equals 0 is not allowed. That means x cannot equal 3. 6 equal to 0 can also be written, but that already is nonsense. So anytime it's just a number in part of your LCD with no variable attached to it, it doesn't have a restricted value. It's just a number that we've pulled out. It's only when we have an x as part of the LCD portion that those cause dividing by 0. So we're going to multiply each term in our equation by my LCD. So there's my LCD. There's my first term. Write my plus sign. Write my LCD. Times it by that second term, that second fraction. Write my equal sign. Write my LCD. Times it by that last fraction, the one on the right side, the 5/6. Notice every term, 1, 2, 3 different terms that we have on both sides of our equations has been multiplied by the LCD. What's going to happen if you picked your LCD correctly is that this should do some cross reducing. 3 goes into 6 2 times, so we're just multiplying 2 times -5. So that's going to be a -10. X minus 3 cancels here, so we're just doing 6 times 4, which is 24. The 6 cancels here on the other side, so we get a 5 times an x minus 3. Now, this equation is not the exact same equation as the original. This is what we call a similar equation. It's because we've cleared out those parts in the bottom that have those denominator pieces, the x's. And we do that so we can easily solve what's going on in the numerator. So the only catch with this process is that you need to list the restricted value over here first, so that after solving this equation that is similar to our original, we are checking to make sure we don't have a bad solution, okay? So if we add those together, they're like terms on the left side. That's going to be 14. Distribute the 5, we're going to get 5x minus 15. I can add 15 to the other side. That's going to be 29 equals 5x. And we can divide by 5 to get the x by itself. So that's going to be 29/5. And that should be reduced. There's nothing that goes into both of those. And that is not 3. So we're okay on that front. Okay, on one like this is kind of a special case. Since this is just a whole number, I would probably move this over and subtract it to that side and get 0. You can write 0/1 if you want. Then this is a proportion problem. If it's something simple enough like that where you can move it over, I would honestly do that. Since this isn't a fraction and neither is this, they're both just numbers. We could still write our restricted value, the undefined value here. That would make our denominator equal to 0. Would be -11 when we move it over and divide it by 2. So that's going to be x cannot be -11/2, okay? But what you're going to see on this one is when we go to cross multiply, we get 6 times 1 equals 0 times 2x plus 11. This times 0 zeros everything out. This is what we call a nonsensical equation. 6 can never equal 0. So anytime you are solving a problem and all of your x's cancel out while you're solving, either you're going to get a true statement that's always true, or you're going to get a nonsensical false statement that's always false. If you get a statement that's always true, that actually means every number on the number line except this restricted value would be a solution to your original equation. If you get a nonsensical one, that means that you have no solution. So either, like if I had 6 equals 6, that would be true forever. That means every number other than -11/2 would work. But if you get a nonsensical equation like 6 cannot equal 0, then that means there is no solution to this equation at all. And we sometimes like to put in the word no real solution, just so they realize we are talking about the real numbers. All right, let's look at E. So I would factor all my denominators first before I try to get my LCD. This is already factored. This is already factored. It's this perfect square one in the middle. This is a 2u plus 3 and a 2u minus 3. They're both perfect squares with a minus sign, so it's going to factor. But luckily, those are the other factors we've already seen. So my LCD is I need 1 2u minus 3 and 1 2u plus 3, because we never see more than one of each type in either of our denominators. That means my restricted values, you kind of get used to this after a while. We set it equal to 0, so I'd be adding 3 and dividing by 2. My other restricted value would be subtracting 3 and dividing by 2. So I can't have 3/2 or -3/2 come up as a solution. Once you've got that determined, you're going to multiply every term in this equation by the LCD. So 2u plus 3, 2u minus 3 times the first fraction plus sign, 2u plus 3 and 2u minus 3. Again, it doesn't matter which order we write those two factors in, as long as we have them both, times our 10 over, notice I'm going to keep at the bottom in factored form so we can see what cancels, equal sign, LCD, and this is legal, remember, because we're doing it to everything on both sides. And we're also writing down any possible restricted values. So the 2u minus 3 is going to cancel in this first one. So we'll have 4 times 2u plus 3. I will work that out in just a second. Both of these are going to cancel in the middle term here. So that's just going to be a plus 10. And the 2u plus 3 cancels in the last one. So I have a 1 times a 2u minus 3. So distributing, we get 8u plus 12 plus 10 equals 2u minus 3. Add like terms on the left side, that's going to be plus 22. Subtract 2u over, that'll be 6u. Subtract 22 over, that's going to be a -25. So -3 minus 22 more. And divide by 6. So 25 over 6, -25 over 6 doesn't reduce. It is also not one of my restricted values. Okay, let's look at the next one. Be careful here, these two x's do not cancel because this is a monomial and this is a binomial. I always try to point that out when I see it so students don't make those mistakes. Neither do these 6's cancel or reduce in any way. So I'm going to pull out a 2 on this and we'll have 2x plus 3. You could technically reduce the 6 and the 2 we pulled out to the front if you wanted to. But I'm just going to, for the sake of just showing you the LCD method, I'm just going to work it out from this point. So my LCD, I need to make sure I have every number or binomial represented. So 1 and 2, the thing that they go into is 2. And then a 2x plus 3. So that's going to be my LCD, which means my restricted value. This doesn't give me any restricted value since there's no x on it, but this would be that x cannot equal -3/2. So we're going to multiply each term by that LCD of 2x plus 3 times the first fraction plus, so my plus sign, 2 times 2x plus 3 times my second fraction. Keep the bottom in factored form so you can see what cancels, equals 2x plus 3 times the 5 over 1, or just 5 if you don't want to write that as a fraction. Okay, so in my first one, my 2x plus 3s are going to cancel. That's 2 times 2x, so that's 4x. The second one, everything in the denominator cancels, so that's just going to be a plus 6 on top. This side, we're going to get, you could reorder this if you want. This is 10 times 2x plus 3 because we can multiply the 2 and the 5 together since they're both monomials. So that would be 20x plus 30. Subtract the 4x over, that's going to be 16x. Subtract the 30 over, that's going to be -24. You can check that on your calculator. So 6 minus 30. Divide both sides by 16. Now, if you just circled this, you have to be careful. This is a reducible fraction. So we divide that by 8 on top and bottom. That ends up being -3/2. So this is where you would get yourself into trouble if you didn't write your restricted values at the beginning. This is not allowed. This is an extraneous solution. It's something we found by solving an equation that was similar to our original, but because we cleared out those troublesome denominators that had the restricted value, that original equation we started with, part F, would not let us plug in a -3/2. It would make both of these denominators dividing by 0. So that means there is no solution to this problem. Even though we were able to solve it, it was a restricted value. All right, and then I have just a couple more of these before we get into the literal ones. So I'll go through these a little quicker. Factor this, we get a 2x plus 3 and a 2x minus 3 because it's perfect squares, square root of both of those with a plus and a minus. My LCD is 2x plus 3, 2x minus 3. So my restricted values are -3 divided by 2 and add 3 to get that and divide by 2. So remember, you're just setting those equal to 0 and solving them to get those restricted values. Going to multiply both sides all the way across by my LCD. 2x plus 3, 2x minus 3. And then we have our first fraction through the LCD of the next group part. So 2x plus 3, 2x minus 3 times the 4 over 2x minus 3 equals, times it by the LCD, 2x plus 3, 2x minus 3, and times by that last fraction on the right side, 5x plus 6 over the 2x plus 3, 2x minus 3. Okay, 2x plus 3 cancels in the first one, but I'll have to distribute 2 times 2x minus 3. And I don't ever do that right away because the reason is, if this is ever subtraction between these two fractions, I don't remember if I've done much of that. You have to make sure you distribute the negative. So I always do my distributing step after this cancellation step. So I just bring everything down. So this is a 4 and a 2x plus 3. That both are going to cancel on the right side, and that just leaves me with 5x plus 6. So now we can distribute a positive 2 and a positive 4. So that's going to be 4x minus 6 plus 8x plus 12 equals 5x plus 6. I get 12x plus 6 on the left side by combining like terms equals 5x plus 6. It's over here. Subtract the 5x from both sides, we get 7x. Subtract the 6 from both sides to move it over, we get equal to 0. A lot of times students see this and think that is no solution, but 0 on top is fine. This is just x equals 0, which is not one of my restricted values. So sometimes the solution can be 0. 0 is a number. All right, and then the last one before we get into the literal equations, again, I just chose a lot of these that had the perfect square denominator part because that's easy to factor. For the examples, some of these might be trinomials in your homework. You just have to factor it using our factoring techniques. So my LCD is I need a 2x plus 5 to clear and a 2x minus 5. So that means my restricted values are subtract 5, divide by 2, add 5, divide by 2. So -5/2 and +5/2. So for this one, I'm going to multiply everything by the 2x plus 5 and the 2x minus 5. Actually going to go ahead and pre-prep, write that out because it'll be quicker than changing the colors multiple times. And then my first fraction, my plus sign, my second fraction, my equal sign, and my last fraction. Okay, so in this first one, the 2x plus 5s are going to cancel, so we'll have 2 times 2x minus 5. Plus, in the second group, we'll have the 2x minus 5s cancel, so that'd be 3 times 2x plus 5. On the right side, the whole denominator will cancel, so we'll just have the 10x plus 5. So this is 4x minus 10 plus 6x plus 15 equals 10x plus 5. This will be 10x plus 5 equals 10x plus 5. The first thing we normally move is the x's. If I go to move these x's over, they're going to both cancel out. When I go to subtract, I just get 5 equals 5. This is another special case. Remember earlier we had, if you get a nonsensical equation like 6 cannot equal 0, that means you have no real solutions at all. If you get a true statement and all of your x's canceled out while solving, and so 5 equals 5 is a true statement, that means it's all real numbers are solutions, except in this scenario, you cannot use the two restricted values. So all real numbers except x equal to -5/2 and +5/2. So it's anything other than those two numbers. So every other number on the number line would plug into this equation and have a true left side equals right side relationship when you check it. And that is something I'm not modeling in this video, is that you can go through and check your solutions. I oftentimes recommend maybe writing that you're doing a check off to the side and show plugging in the numbers, but then use your calculator to help you check them, because that way you're not taking too much time from your next problem when you're doing a test. All right, so we've got a few more of these. These are the literal equations. This is when you're resolving an equation for a different variable. There's some general rules here. If you see more than one of the thing that you're solving for, you're most likely going to have to do what we call a regrouping of your terms. And anytime you have denominators, you want to go ahead and clear those and get that out of the way so that you don't have fractions that you're trying to solve for in the middle of the process. So we're going to cross multiply, since this is like a b over 1, that's one fraction equal to one fraction. So I'm going to have capital B times 1 minus a. And you do have to be careful with WebAssign. If they do b as capital, you have to do it as capital. If they do a as lowercase, you have to type it in as lowercase. And then a times 1 is a. I'm trying to solve for a. This is a, but I still have another a. So I technically haven't solved for a yet. I'm going to have to get, that's what I meant by regrouping. So redistribute this to get all the terms out of their parentheses. We're going to regroup the a's together by putting everything that has an a on one side and everything that doesn't have a on the other side. So I'm going to add the AB to the right side to be with the a. Why we do that is because now this is a GCF for this side. So I can factor out an a out of this pair. That would be a divided by a is 1. AB divided by a is just b. And then now we have a single a in our equation. Once you get to having one of the thing you're looking for, you can isolate it. So I'm going to divide over the 1 plus b. And you can write this like this, or you can write it like this, as long as you have all of your signs correct on each part. Okay. For the next one, we're trying to solve for I. It looks like it's also set up as a cross multiplication kind of problem. So that would be Ri equals V times 1 is just V. I might make that look more like a 1. And then I'm solving for I. So there's only one of them, so I can just divide over the R. So this one's a pretty quick one. Okay. Notice this one's a little more complicated. I have Q that I'm trying to solve for, and I got a couple Q's. So I'm again going to try to clear this out. I might go ahead and distribute what's going on in that denominator first. It's a little weird looking. So I would have Q plus P, because P times 1, and then a minus PQ. Just a little bit less intimidating than seeing that parentheses in there already. Then we're going to cross multiply. So we have S times all of that equals P times 1, so just P. We need to get all of our Q's to have their own terms. So we have to distribute this to make sure we can figure out what has a Q and what doesn't. So SQ plus SP minus SPQ. So I've distributed that capital S to all of those equals P. And then I have two terms I'm going to underline, if you notice, that have the Q letter. So I need to move the SP to the other side by subtracting, since it's a positive. So I'm going to have my SQ is still over here. So is my SPQ. I'm going to have my little p over here, and I'm going to subtract from that the big S little p. Then I'm going to pull out that common factor of Q. That was the whole point of getting these isolated on the same side together so that they are a greatest common factor. I know there's also an S in common, but we're isolating for Q. So that'll be S minus SP equals the P minus SP. We'll divide over the S minus SP. So this will be Q equals little p minus capital SP over little s minus capital SP. And again, you cannot reduce those. You cannot reduce those SPs because that's two different binomials on top and bottom. All right, and then the last one for this video, sorry if it went a little long, is this one. We're trying to solve for t. So I don't have just a single fraction on each side, so I'm going to use an LCD of r, s, and t. I'm going to multiply everything by r, s, and t, which I'm just going to show my work right here. Multiply each term by that so that I can get everything out of the denominators first. So in this first fraction, the r is going to cancel. So we have st times 1. So that's just going to be st. And the second fraction on the other side, we're going to have the s is going to reduce out. So that's rt times 1 minus the t is going to cancel out in the third fraction. So it's just going to be rs. Now I'm trying to solve for t, so I need to get my t's on the same side. So I'm going to subtract the rt over since this t is already on this side. So st minus RT equals negative RS, since that's still negative on that right side. I can factor the T out since now I have everything with the T on the left of those two terms, and then we'll divide to get the T by itself. And you can put that negative on top, or you can put it out in front of the fraction. It should be okay either way. All right, that is the end of that video.